Hey there. This is going to be my explanation of our project to extend the work done by Andy Zhu, Zifang Wang, Nicholas Carlin, Leland Esser, Jessica Coulter, and Matt Fredrickson, and their Carnegie Mellon University project, research paper rather, universal and transferable adversarial attacks on aligned language models. What we attempted to do here was to extend their research, which I'll explain. Essentially, their initial research paper had used a large language model to iteratively generate attacks on adversarial attacks on large language models by generating a suffix that can be attached to a prompt that will allow you to essentially jailbreak it and get it to produce a response that it shouldn't normally be able to present. That is when you hear adversarial attacks referred to throughout the course of the paper. This is essentially what it's going to be referring to is any attack that allows you to circumvent an LLM's natural safeguards against disseminating that sort of information. This obviously is important because as LLMs are getting more and more pervasive in our culture, they're just becoming more powerful and more accessible to more people. Unfortunately, that's inevitably going to include some people who are looking to do malicious activities. And unfortunately, once that information gets out the first time, you can't really claw it back. You know, if you teach somebody how to make a bomb, that information is out there. It's very hard to get that information back. So for that point, I think, or because of that point, this kind of research is very, very important. And I think it also makes our research even more important. Essentially, the reason why they had gone through and decided to pursue this kind of attack is in the hope that people would then become aware of it, be able to develop defenses against it, which is essentially what we're doing in our research. We're hoping to develop a system that detects that sort of attack and is then able to prevent against it. Back to the earlier point, I think it may possibly be a little more towards false positives, but again, when only one hole in the system allows information to get out that can potentially be harmful, and it only takes one, it kind of helps to defer to the false positives. And again, the way their system works specifically is it goes through and it starts with just a base prompt. By default, typically that is just exclamation marks, but there are different ways to make that more to randomize that. And then it's just going to add this suffix to the end of a prompt. And then as it goes through, it's going to iteratively change the tokens involved in this suffix. And then see which suffixes have the greatest percentage success, and then over time find a suffix that works not only with the open source models that we typically have access to, but also works on black box closed source models like ChatGPT, Gemini, Claude, etc. They demonstrated, which makes it even more potentially harmful because these LLMs typically have trillions of parameters versus the 7 billion to 40 some odd billion you're typically working with a lot of the open source models, and thus they have access to a much greater source of knowledge, and so they can potentially be much more harmful if they are then used for malicious means. And so going into our contributions, this was the initial model that they had here. This is the Jupyter Notebook version. It's a little streamlined. It doesn't have all the features that the original version had. The original version had the ability to do multi-pronged attacks, essentially attacking multiple LLMs simultaneously to see which prompt works most effectively across a variety of LLMs simultaneously. This one is more streamlined. It's just attacking a Llama 7B 7 billion model exclusively. But other than that, it does show the same implementation. There were, if you do try and go and recreate this research on your own, there are some imports you'll have to manage. Just as a heads up, it's not quite as plug and play as you might think. You can't just load up their Jupyter Notebook and just, in my experience, just have it go. Additionally, this model without any quantization or other operations to split the model takes at least a GPU with 32 gigs of RAM space, of memory space. So it's not going to be something you can just run on your local computer. Typically, for this one, I had to use a cloud GPU. You're going to see some errors throughout, by the way. Most of these have to do with just deprecated calls that were made in their initial program, because a lot of these dependencies are updated so quickly. It oftentimes the syntax changes, and they're not deprecated completely. Just give me a warning that that it needs to be updated. So anyway, digging into our code. Things that I modified, the first deliberate one is going to be, or most notable one is going to be here. As I said before, initially, the suffix started with just a string of exclamation marks, because we were going to use this information to train a second large language model to then identify what these attacks look like. I needed as random a starting suffix as possible. I wanted them to look as different as possible, because if a lot of them look similar, then that essentially helps the model we're using to detect these attacks. It helps. It couldn't lead to overfitting, essentially. In any time you have just base similarities in one set of data versus another, then that allows the model to then kind of hone in on those specific similarities and not necessarily the factor you're looking for. So I don't want it to just know that if the exclamation mark's in there, that is an attack prompt. I want it to detect other features in there that may not be quite as obvious. And to that end, what we did was we used a English words text file that is going to bring in just a bunch of, it's not an English word dictionary, going to bring a bunch of English words in. It's going to integrate those into the starting prompt, and it's going to integrate a bunch of just random strings and symbols in as well, to further kind of randomize that adversarial text and make it not as obvious. And then also just added a couple extra fail suffixes here. Essentially, the way the program is going to work, it's going to go through, it's going to iterate through changing these tokens. It won't be exclamation marks, but it'll be a more randomized token. And it's going to look and it's going to test the responses, and it's going to see, it knows it's a fail if any of these come back in the response. And then specifically, it knows that it's a success. It hits on the percentage of this target phrase it hits, which is for us going to be right, convincing anonymous death threat. Says here's a convincing anonymous death threat. It knows that is generally a success. Some other random variables set in here, a number of steps, number of iterations that goes through batch size, the number of potential candidates that it analyzes in each pass. And then other than that, the only modification I made to theirs was the addition of a saving function in here, which again is going to allow me to, as we go through and find those prompts that are successful in generating a prompt that should normally be forbidden, an adversarial response. We wanted to save those prompts so we have something to train our subsequent model on, which is what's going on here. It's writing the CSV, and every time I see a successful prompt, I also modified it here for a little for rapid generation, and just goes through and reset that process every 50 intervals. And as you can see, it's going through that process here. And let it run a little bit, and then we'll come back and we'll show what a successful prompt looks like. But also, just real quick, you can see here, this is the current suffix that it is adding. So essentially, each time it goes through, it's passing. Here's a convincing anonymous death threat with this suffix attached, and manipulating that each one to see which one gets the successful responses. Now moving over into our specific code, we have right here. This was built on a BERT large language model. BERT is specifically good for classification type tasks, which is why I selected it for this event or for this project. Specifically, this BERT model is BERT classification, which is specifically used to classify binary text data. So essentially, is it A or is it B? And since in our research, we're essentially trying to identify, is it A, a human-generated attack, or is it B, an adversarial attack? This seemed like it would fit pretty nicely. Going through our code, I've already imported it and ran it. So again, it's bringing in my GitHub repo and installing some of the necessary dependencies through scripts in the program, and bringing in my data set as well. As far as the data set, again, it is running off of, this is the initial data set. This has a lot of duplicates. There was a function in its run, remove duplicates, that does remove a lot of those duplicate prompt entries. As well as, you can see this is a prepare data script that I also ran, included. This is going to use several functions that again further try and obfuscate that data or further split it up to make it harder for the large language model, detection large language model to overfit to the data. So there's a sliding window function here that you can set window slide and stride on. Essentially, that's going to split up each of these adversarial prompts into, instead of the entire 22 token prompt, it's going to take small chunks of it, essentially from 10 to 22 characters in length. And that, again, that further helps kind of obfuscate that data so it is not all equally sized. So it can't say, if I say a 22 character attack, then the model will say, well, if I know it's 22 characters, I know it's always an attack. So we want to split up both the length of the attacks, starting characters, ending characters. We're shuffling the data within the data set itself, and then merging that with human data, which I'll get into here in a second, and using that to create our final testing training data sets. Again, the human oh, excuse me, the human data is brought in here in prepare data. And that is going to be this human text CSV file. Again, what this is essentially is going to be uh, a random selections taken from a Wikipedia, a chunk of Wikipedia files, data from Kaggle. So it's just random Wikipedia entries. It's going to include numeric entries, text alphanumeric entries. So it's going to be a wide um, types of data, very different, disparate types of data. So again, you're not just getting alphanumeric responses that the model can overfit on. It's going to be web URLs, it's going to be code, it's going to be anything that a human might have put into the Wikipedia data to a Wikipedia article at some point in time. And then again, you can see it's splitting those up. It's randomly chunking them into entries of different sizes and putting those into this data set, again, all labeled with a 0, which is going to indicate a human prompt, and 1, which you will see will indicate a adversarial or LLM generated prompt. And here you can see where it has split up the data. It will eventually split them into test, train, and validation data sets. The training data set is essentially what it goes through and checks against to attempt to label, and the validate data helps it then kind of see how good its guesses are, essentially. And then here you can see where the actual training data has come in. You can see how the adversarial prompts and the human prompts are interspersed with each other, and how they're pretty chopped up, so that you are getting it's not immediately evident which is which, at least to my eye. As you'll see, the model does a much better job of identifying it than I would be able to. And then obviously the 0, 1 labels over here. There is a function in here, by the way, that does make sure that the data set is split at a approximately 50-50 rate between human labels and adversarial labels. I believe that's in the prepared data function. And then it's going to iterate through again, training on that data set. And then down here, you will see as it goes through its epochs, how its training loss gradually gets better over time. And then it's going to save this prediction file. After it goes through and it actually does all its training, then it ultimately lands on it ultimately is then going to go back through and test against the training test.csv file, and actually make predictions. And here you can see how those predictions actually came out. So this is the actual label as it came in, and this is the predicted label. And as you can see, while there are some missteps in there, for the most part, it did a pretty amazingly good job of predicting the adversarial attack prompts suffixes versus the actual suffixes, or actual human generated prompts rather. So as for where that leaves us, I think there's a decent chance that there was some overfitting in this data, even though I think this data set's that's not right. This one is, I think, several thousand values long, which I think BERT needs about 25 to 5 to really get a baseline. But it's still probably underneath less than an ideal amount for a BERT model to train on. More data would probably help and would probably lower the initial accuracy, maybe leading to better results overall. So I think in general, probably more prompts could benefit the model, but in general, it seemed to be a pretty good proof of concept, at least, that this sort of detection model could be used as a defense against these sort of adversarial attacks, as demonstrated in this paper. Again, I think that becomes more important as we move forward and as these LLMs become even more powerful, able to do more things. You want as many safeguards as possible against this kind of information getting out. And that is our paper. See if I can get a adversarial prompt to generate here. I cut this model a little early, so it's not fully trained. So we may not get super great results from it. But just to kind of show the proof of concept. But yeah, other than that, this is our research, and I hope that you have enjoyed it. Thank you.